מסתכל סיבה. רק דברים טובים. זה גם טובה. לא, רק דברים טובים. מה שלומך? מעולה? איזה יופי.
זהו, אנחנו עכשיו ניכנס לקצת ראשון. אני חושב שזה ממש מגניב, בוא נראה אם יש לי קצת שווה להראות לך. אנחנו מאמין את הרכב שלנו, יש לו חיישני IR, ככה שהוא מתקרב לצוק וצריך לעצור. זה שהוא די פה. אז הגענו ליכולת הזאת.
וואו!
היה קודם שלחנו לו קצת בזווית, ואז הוא כאילו רק ניגש לשולחן, ואז הוא כל עצמו מגיע לקצה, חוזר אחורה, מסתובב, נוסע, מגיע לקצה השני, חוזר אחורה, וכאילו כמה דקה שלמה הוא נסע לשולחן מתחבק וכל זה אפשרי.
מה שדיברתי איתכם זה אחות של עובדיה יוסף, לא של אני פשוט בלבלתי. זה דומה, אבל התכוונתי.
זה הכל חלק מאותו מכלול פס.
וואלה, זה פשוט, הוא ממש נראה כמו דיג'י גדול של דיג'ו.
אז זה ממש מעניין מה שהם עושים. זה מאוד הספיד ההתפתחות השאלות כזאת. מאוד פיזיקאית, כאילו גם השאלות כאילו בלבול חשובים יותר.
אבל אולי זה...
כן, לא יודע. כאילו סוג נישה כזאת. בכל מקרה, הם באמת
חיכיתי מטרה עכשיו.
לא, אבל ממש לא נסתם.
אוקיי.
הייתה לי פגישה, לא סתם. לאכול בשיעור ברשתות.
זהו, זה לא טוב.
Good afternoon. Is someone taking notes today? No notes? Okay. I would like to start by, first, before we go back to what we did last time, discuss a small point about mutual information that I mentioned in the previous lecture, and I need to refine a little bit what I said. What I said was not always correct. So I mentioned to you that mutual information, when you calculate it as a differential mutual information for a continuous variable for a continuous distribution, and you want to interpret it as saying something about the discretized version. Suppose that you would discretize the two variables in bins and then ask what is the mutual information in the discrete version. I said that it's not sensitive to the discretization. Remember that? We discussed it for a while. And it's not always true. So I want to tell you, I will not go into this deeply, but point at the situations in which it's true, and the situations in which it's not true. So let's first remember the one-dimensional case. In the one-dimensional case, if we have some distribution that has some continuous form, and we calculate a differential entropy, we can relate it to the entropy of a binned version, right? And there is an extra between the two expressions. There is an extra log 1 over delta x that enters, but otherwise we saw that we can relate it to quantities, and this relation is correct as long as the distribution is smooth over the scale of the bins, right? Smooth and almost the bins should be small compared to the such that within each bin the probability distribution is almost constant. Now let's think about a two-dimensional variable or two variables. So it's now a two-dimensional probability distribution that involves two variables, x and y. So I don't know how to draw three-dimensional plot on the board, but I just want to plot the space. So there's x and y, and let's suppose that we now discretize this two-dimensional space. And as long as we're in the similar conditions as in here, where the probability distribution within each one of these bins is uniform, then we can do the same tricks. And what happens is that the delta x and the delta y, if we calculate the mutual information, they fall out. Because remember, the mutual information we can write as log. It's log of the mutual entropy of x and y divided by age of x, age and y, and it turns out that the delta x and delta y enter here and here in such a way that they cancel. But all this, and so in that sense, as long as you have the two variables are such that the joint probability distribution becomes smooth over a sufficiently fine scale, once you go to that scale, the mutual information is not sensitive to the discretization, meaning that if you will make more and more fine bins, the mutual information between the bin versions will no longer depend on the bin size. Moreover, it will not depend on even on if you have a non-uniform bin size. If you, in some range part of the variable x or some part of the variable x, you have more fine bins and less fine bins. Once the bins are sufficiently small, it will not be sensitive. But there are situations where it's not true, and it's easy to see why. Remember that we discussed the fact that the mutual information of two variables is bounded from below by the entropy of each one of them. And we know of a situation where this bound is saturated. What is this situation? Can you give me a situation where the mutual information between two variables is equal to the entropy of one of them? When they're equal. Now, we know that as we take more discretized version of the variable with finer and finer bins, this diverges, right? Because this is the differential entropy. Suppose that we take the discretized version. So for the discretized version, this diverges. It's the differential entropy plus log 1 over delta x. But the mutual information of the two variables are the same as this. So this is sensitive to the discretization. The mutual information in this example is sensitive to the discretization, no matter how small the discretization is. But it's, given what I've told you here, you can see why that's true, because in this case, if you think about the joint distribution of x and y, where does it fall? How does it look like? It's always concentrated only on the diagonal. So if you now take bins, you bin it, no matter how small the bins are, you're never in a situation where the probability distribution is uniform within each bin, right? So you're not in a situation where we can evoke the argument that I described above. So just to wrap these things up, there are situations in which mutual information is not sensitive to the discretization, but there are others where it is. So it's a bit more complicated than what I told you. Because x is always equal to y. So there's the only, as long as x is different, the probability of having x different from y, if x is the same as y, is 0. So the probability distribution is like it's a delta function. It's a concentrated on this. It's actually infinite on this line and 0 everywhere else. Okay.
I missed the...
Yeah. Okay. It's not. It's. I think. Maybe you should ask your question, but we will not delve into this. I will answer, then we will not delve into this more because I think this is a side issue. It's not critical for what we're doing in the course. I just wanted to clarify something that I said, but I will answer your question.
Maybe I was trying to write and I missed it. Why? What is the? When is the problem? When is it not true that it exists to this?
So let's say when it is true. When is it true? It is true when the joint probability distribution of x and y is smooth as a two-dimensional probability distribution, such that for sufficiently small bin sizes, the probability will be constant within each one of the bins. Okay, so if you have a scale, some scale of delta x, delta y, such as smaller than that, the distribution will be uniform in each bin. From that scale and smaller, if you make delta x, delta y smaller, the mutual information will not be sensitive to the choice of delta x and delta y. But here I gave a counterexample where the variable x and y are just the same variable. Okay? And in that example, there is never a scale like this. And indeed, in that case, we can see that the mutual information diverges as you make delta x and delta y smaller and smaller, because it's just equal to the entropy of the discretized. It's just equal to the entropy of x, and that diverges as you make the discretized x. Its entropy diverges when you make delta x smaller and smaller. Okay. So this was just so that I said something which I think was not precise, and it was important to clarify this. And now we go back to the question of efficient coding of a single variable with some nonlinearity. So we're discussing an input-output relationship, which we imagine might be implemented by a neuron, which is just a nonlinearity, and we discussed the question of optimality. And last time we rephrased this question, we reformulated it using the notion of mutual entropy. So let me remind you, we had the variable x with some probability p of x, and we transformed it into R response, which is some function of x, which we also called this part for each instantiation of x we call y, plus some noise. And the noise has 0 mean, and we allowed the variance of the noise to be some function of y. Meaning that depending on the output of our imagined neuron, when the output is close to saturation or not close to saturation, the variance of the noise might depend on that. And now our goal is to maximize the mutual information between x and the response. So the response involves both x and the noise, but we don't care about the noise. What we care about is that the neuron will convey as much information as possible about the input. So that's why we want to maximize the mutual information between R and X. Under a constraint, as before, and the constraint was that f of x lies within some interval. We chose it to be 0 up to some R max. Okay, so now we just need to write down what this is, right? So the mutual information of R and X can be written as the entropy of R minus the entropy of R conditioned on X averaged over the distribution of X. Okay, so let me keep the first term as it is for now, and write down what this is. So what is, I forgot to mention that Xi is, we assume that Xi is normally distributed. And is independent of X. I will not write this explicitly. So what can we say about the distribution of R given X? We already did it, but it's a normal distribution with mean, which is f of X, but the mean of a normal distribution does not affect its entropy. So this is just the entropy of a Gaussian variable with this variance. So and it's independent of X, because the only thing that X affects is the mean. So for all values of X, it's the same. This is the same entropy. So I can just write. Sorry, but it's not. But sorry, X affects the mean, but it also affects another thing. It affects the variance. So now, in contrast, actually, to what we did last time, the entropy. This entropy does depend on X through this.
So how can the noise be independent?
So no, you're right. It's not independent of X. It's just the mean. The mean. The mean is. You're absolutely. It's right. It's not independent. What I said is I just forgot for a moment that we're doing this. It's not independent. The noise is additive, and R is just the sum of this and this. And what we assume is that this has zero mean, and the variance that depends on X. We wrote it as a function of Y, but it's just another way to write the dependence on X. Yeah, so they're not independent, absolutely. So now we need to write here the entropy conditioned on X. And we need to average over X. So I will write an integral over dx, P of X. This is just the averaging over X. And I will add now, multiply this by put here the entropy conditioned on X, which is half ln 2 pi e sigma square of f of X, right? Because sigma square depends on f of X. Now, in general, optimizing this quantity might be complicated. Depends on the distribution of X, depends on this function. We'll not go further in a general approach to this, but we will consider a particular case where we can understand how this thing behaves and what it tells us. So what we're going to do now is consider the low noise limit. Where sigma square becomes very small. Okay? Now, we still are going to allow it to go to 0 in a way where it's not uniform. It doesn't have to be the same for all values of y. But I just assume that it's sufficiently small. So one way to formalize this, which I will not write explicitly, is to say, let's suppose that you put in front of this some parameter alpha. So you now have some parameter alpha times the function of y, and now you take the limit where alpha goes to 0. Okay? And we ask ourselves, what can we say about these expressions? And one thing to note already from this expression is that we can't just, ignore sigma in a very simple-minded way, because here you have a log of sigma, and this thing diverges when sigma goes to 0. So we can't just replace. You can't say this function goes to 0 or it goes to. It's not as simple as that. So let's see what we can do. So what I want to point out is that the response R is equal to y plus something which is now very small, because the noise, as we take the limit where the noise, the variance of the noise goes to 0, the difference between R and y is of order sigma, the standard deviation of the noise. Right? And for that reason, as we take the limit where sigma goes to 0, P of R approaches a P of Y, or P of Y, yeah, P of R approaches P of Y as sigma goes to 0. And therefore, in this term, we can consider this limit in a very simple way by just saying that the entropy of R approaches the entropy of Y in this limit. Okay? But in this term, we cannot do something so simple because when sigma goes to 0, this thing actually diverges. So we will keep this term as it is. But you will see that once we write this, the problem becomes very simple. So, so the entropy, the mutual entropy, the mutual information of R and X is equal approximately, or let's write it as an arrow where sigma goes to 0. It's the entropy, the differential entropy of Y now. Now, another thing is that I can now do here a change of variables. X and Y are just related to each other through this function, which is written here. Y is f of x. And what do I need to do when I change variables? So remember what I told you last time. The important thing to remember is that P of x dx is the same as P of y dy. That means that in a small interval x to x plus dx, the amount of probability is the same as an amount of probability in the corresponding interval of P of y up to y plus the corresponding dy. So this becomes, I can rewrite this as an integral dy P of y. And that's nice because here I also have y. So I have here ln 2 pi e sigma squared now of y. And you can see now that everything now is written in terms of P of y. This is written in terms of P of y, and the entropy of y is also in terms of P of y. So this is nice. And what we want to optimize is this. So now we view all this as a functional of P of y. And we will optimize in terms of P of y. Now P of y has a constraint in it, as just as much as it had when we discussed this without the noise part. So P of y is constrained such that the integral of P of y is 1. So we can what we need to optimize is some optimization function, some functional of P of y, which is the mutual information, which is this, minus a term which involves the Lagrange multiplier, which is the integral of P of y dy minus 1. This is our constraint. And now we can do a functional differentiation. So we write that the derivative with respect to P of y should be 0. And so maybe I should actually write down this function. So before I do this, I will write down the function. So this is minus integral P of y ln P of y dy. This is s of y. And then we have minus half integral dy P of y ln 2 pi e sigma square of y. And then we have minus lambda integral P of y dy minus 1. Is it okay if I write here? readable? Because I don't want to. So I will do this. So now we want to write a delta L to delta P of y is 0. So when we take the derivative here, we get two terms. One is when we take the derivative of P of y, so we get minus ln P of y. One is when we take the derivative of a ln, and that just gives us minus 1. And then here we will get ln 2 pi e sigma square, half ln 2 pi e sigma square of y. And from here we'll just get lambda. And all this is equal to 0. So what we got is that ln P of y is some constant. That constant is minus 1 minus lambda. Minus, I can also open up this ln, and there will be half ln 2 pi e, which is also a constant. So I'll put it into the constant. And then the interesting part is the minus half ln sigma square. And I can also write it just as minus ln sigma, because ln sigma square is 2 times ln sigma.
Log, you don't derive the ln with respect to
No, because remember, what are we taking the derivative with respect to? With respect to p. So here, p does not appear. This is not the probability distribution. P of y does not appear in here.
so the sigma doesn't depend?
No, sigma was given, right? We assume that there is a certain amount of noise for any value of y. This is not a probability distribution of y.
It doesn't depend on it?
No, this was given. This is fixed. We're not. Our rule within this formulation. This is fixed. This is not something that we're varying. What are we actually varying? What we're actually varying is this function, right? We're trying to find the best input-output relationship. And we took the similar approach also when we discussed just optimization of the differential entropy, that instead we can say there is a mapping between f of x and p of y, right? There's a p of x goes through this transformation, and that defines, that is what determines the probability distribution of y. So the approach that we're taking here actually is that instead of explicitly taking writing this as a functional of f of the function f, we're saying something a bit different. For any function f, there is a probability distribution of y, p of y, and let's find what is the best probability distribution of y, and from that we will infer backwards what is the best f. Okay, but what we're varying is so what we're in this picture we're just varying p of y, while this is kept fixed. This we're not allowed to modify this. We're assuming that there is a certain amount of noise in the system that depends on y. And this dependence is fixed.
Function of y, the integrate of y.
No, but I'm not differentiating with respect to y. I'm differentiating with respect to p of y. Okay, so there is the variable that I'm varying is how much probability falls in every possible value of y. That's the that's what we're optimizing, and this is kept fixed all the time. The relationship between y and the noise, the variance of the noise, is kept fixed. So it's always important when we do this kind of presentation to ask, what are we keeping fixed? We are keeping this fixed. We are keeping p of x fixed.
Fixed with respect to y.
Just fixed. There's a relationship.
Function of y, it's not fixed.
But y is not, there's an integral over y. Y is just an integration variable. Okay, there's...
Y is a function of...
Yeah, but here we're integrating over all values, possible values of y. It's not... while it's true that y is a function of x, but also p of x, x has some distribution, and that distribution is fixed. In this integral, this is an integral of y, p of y times this thing. In this integral, there is nothing that, as we vary p of y, there is nothing that changes in here. Okay? We can discuss this more later if it's not clear. I see that it's not yet clear to you, and maybe for some other people, so this is important to understand it. But I think that now it will be difficult to clarify it more in this way. Okay, so let's I'm taking the functional derivative, and again I just want to remind you there are some constants here: -1, minus lambda, minus half ln 2 pi e. But there is a term which is interesting, which is not a constant, which is minus ln sigma of y. It was squared, it matters, but there was a half in front, and that's why the square does not appear here. Okay, so now we find what is the probability that we want to have for y. With the optimized choice of the input-output function, it should be such that the distribution of y will be some proportional to 1 over sigma of y. Right? If we exponentiate this equation, we'll get p of y is equal to the exponent of this multiplied by 1 over sigma. So the exponent of this is just a constant, and it has to be set such that the probability distribution of y will be normalized. This was our constraint, so I'll just call this constant z, and it's a normalization. We know what it is. It has to be set such that the integral of this thing will be 1, and this is our result. So this is not exactly what we want yet. What we want is f of the function, the input-output relationship of the neuron, but we can infer it now from, if we know what is the probability distribution of x, we can find what is the input-output function that will generate this probability distribution of y. This is also what we did when we just optimized the differential entropy. When we optimized the differential entropy, our result was that this should be just constant. Now you can see when we have this more when we have this formulation which is based on a more careful thinking about the problem, what are the conditions where we'll still get a uniform y? What are these conditions? When will p of y be simply a constant? When sigma is not a function of the noise. So if sigma is independent of y, we get back the result that we got last week. Or did we get last week or Tuesday? Tuesday. That p of y is simply uniform. Okay? So, and that makes sense because we discussed the fact that the noise has a similar interpretation as the way in which we're discretizing the values of y. If the noise is uniform, we know we can measure, when we measure r, we know something about y with equal error in every possible range of y. That's similar to a uniform discretization, and that's why the differential entropy, which implicitly implies uniform discretization, was relevant. Why optimizing the differential entropy led us to this result. But you see now that if the noise depends on y, then we're no longer getting a uniform distribution. So if sigma of y depends on y, what we actually get is that under the optimal transfer function, or in nonlinearity, p of what should be uniform is p of y times sigma of y should be uniform. which intuitively makes sense. It tells us that our encoder wants to put more probability in those bins where there is less noise. Our encoder, if the noise depends on the output, then to maximize the mutual information, those bins that have lots of noise, we want to put there less probability, because these bins are somehow less informative. We want to put more probability in those bins where sigma is smaller. Okay? More probability in bins with less noise. So if we think now about Simon Laughlin's paper that we discussed on Tuesday, he just said the assumption is that these second-order neurons in the fly retina are optimizing the differential entropy of their output. That doesn't make so much sense. What he actually was doing, even if we didn't understand this or didn't say this explicitly, that we can interpret it as maximizing the mutual information between the output and the input, but under an assumption. And the implicit assumption is that the noise in the output noise in these neurons is independent of their output. This is something that in principle can be measured. Okay? I suppose that people have done it, but I don't know what is the answer. One can measure how noisy the output of the neuron is depending on its output, and if it depends on the output, then one needs to refine the theory, and the theory will give a slightly different, or maybe highly different prediction than what it gave if you assume that the noise is uniform. Okay, so far we discussed a single variable, a single input-output relationship. I want to briefly highlight some general lessons from what we did, and then we'll discuss additional, more interesting scenarios where we have multiple input variables. But I want to highlight some of the general lessons that we learned already from what we've done. So we're discussing how one might make predictions about the encoding in a sensory system based on the notion that it's maximizing information about the sensory inputs. And one thing which is extremely important is the natural statistics of the inputs. You cannot discuss optimizing information or mutual information with the inputs without knowing what are their statistics. And if you think that the biological system is optimized for the conditions that the animal encounters in nature, then you have to consider what are the natural statistics of the variables. Here, this was what we called P of X, right? And for different P of X's, we will get different predictions for the input-output relationship. Another general thing that we always have to think about when we're discussing optimization principles, which we will continue to do, is what are the constraints. So here we had two constraints. One is technical. The technical constraint is that played a role in the mathematics is that the probability distribution is normalized, that the integral of P of y dy is 1, the integral of... But the more interesting constraint here was this one. So we had to assume something about our output neuron, that it had some limited range of outputs. This might also be, this is also a question. I mean, and if we did not have this constraint, if R could be anything, our whole optimization scheme would be meaningless. We could use a function. For a given amount of noise, we could take the mutual information to be maximal. We could have by just spreading the response over a very large range. So this constraint was essential. And oftentimes, when we think theoretically about a biological system, we hypothesize some constraint, but it's very difficult in biology often to be sure what is the correct biological constraint. Why it is there. We can have some intuition about what it might be. But also when you read papers about optimization principles in biology, you have to remember that a lot of times the structure of the result that one gets is intimately related to what one assumes implicitly or explicitly about constraints, and therefore sometimes the whole essence of the result is buried in the assumption about the constraints. Yes, that was a question?
I'm not sure where do you use it.
Well, it's a good question. Where did we, well, it actually comes about when you relate this to the function. What we really want to find is the function f of x that relates the input to the output. And so the way to see it is to go back to what we did for the differential entropy, because here I'm just skipping that part, where we use what we do. In the case where, say, the noise is uniform or just maximization of differential entropy, we got the conclusion that P of y has to be uniform. Now, if y has no bounds, then that would just mean that it's completely spread over all values, and that's not an interesting result.
But it's not a result, because it cannot have a distribution.
Yeah, exactly. So then what we do? We say P of y actually is constrained to be between 0 and r, so P of y is like this within this range, and that led us to the conclusion that f is a commutative distribution function of P of x. And in this case, it will not be the cumulative distribution function because you have to take into account also sigma, but it will also be something similar. It would be an integral involving P of x and sigma.
From 0 to r.
Something like that, yeah. No, the r entered differently. It was actually prefactor. So in the uniform case, what we got is r max, integral from minus infinity to x, p of x prime, dx prime, something like that. Or maybe here it's, yeah, that's what we got. Anyway, constraints are important. Another ingredient in the theory which is very important, and this really we realized at the end of Tuesday and in our discussion today, is that what we assume about noise is very important. And this will be the same when we discuss more complicated situations where we want to maximize information in a sensory system. Our assumptions about noise are extremely important. So this really highlights, all these elements highlights things that one needs to put into the theory, and they affect the outcome of the theory. So on one hand, as you will see both here and what we do next, the theories involving maximization of entropy seem very general. They seem theories that have very little place for playing with parameters. Because all we are assuming is that the brain maximizes information. But there actually are parameters. When we formulate the theories, there are parameters that are buried in each one of these elements. And you can say, okay, we can measure these things. But there are always questions about this. What exactly do we mean when we say natural statistics? We measure under some controlled conditions. Is this really very general? Constraints is even less clear. Structure of noise, we're modeling it in some way. We don't know exactly what is the structure of the noise in the biological system. So this is highlighting some of the places where theories involving mutual information actually have parameters in them. And on the bright side, it's a very simple, we're using a very simple argumentation. All we're discussing is the all we are assuming is that the brain maximizes information. There is no task involved here. There is no function or no function other than representation of information. And nevertheless, as you saw in the case of the Laughlin's paper, this predicted well the structure of the input-output relationship, and you will see that this argument predicts well many other aspects of responses in sensory systems. So I will just say what we will start to do next week. What we will next consider is the fact that in most sensory systems, the input is very high dimensional, and our model system all the time will be vision. So in vision, the input is the visual scene, which is a function of position. The first stage of processing, it's discretized by the photoreceptor array. So we can say that the dimensionality of the input is the number of photoreceptors. It's actually even more complicated because the input is time dependent. So if you take that into account, the dimensionality of the input is the number of photoreceptors times the number of time bins that occur in the stimulus. But in most, just for simplicity, in most of our discussion, we will ignore the time dependence. But it's a very high dimensional input. So what?
When you assume that the number of there is no redundancy.
Well, there is a redundancy, but the initial raw number of inputs to the nervous system is the number of photoreceptors, right? Each these are the input units. Of course, they have a lot of redundancy between them, and this is what we will argue that the retina exploits in order to represent the information in a more efficient manner. So there is a very high dimensional input. In the retina, there is also a high dimensional output, the number of ganglion cells. So the retina has photoreceptors. These project to a second layer, which are called bipolar cells. These project to a third layer, which we call ganglion cells, and the ganglion cells send their axons to the brain. And there is a reduction of about a factor of 100 between the number of inputs and the number of outputs, but they're both huge. So we want to discuss what our arguments of efficient coding tell us about these situations where you have a large number of inputs and possibly a large number of outputs. So this is what we will start to do next time, and this is connected, and maybe I'll just mention it, this is connected to, technically, you will see that this will lead us to concepts which also occur in context other than information theory. So we have a large number of inputs, and we have a smaller number, typically a smaller number of outputs, and therefore we're performing what is called dimensionality reduction. Large number of inputs to smaller number of outputs. This is something that we often need to do also when we just analyze data. We have a large number of variables that we measure. We want to make some sense out of them. We want to represent them with a smaller number of parameters. So this is called dimensionality reduction. And you will see that by postulating that, say, the retina represents information about the inputs efficiently, this will naturally lead us to some standard approaches to dimensionality reduction. Okay, so start that on Tuesday. כאן אני דיברתי על זה שאם אנחנו מקטין את סיגמה, נחשוב על זה, בוא נגיד חוקי המשחק שיש איזשהו קשר בין סיגמה ו-y שהוא קבוע. ואנחנו שואלים מה שמותר לנו לשנות את הפונקציה. ואנחנו שואלים מה איפה אופטימלי תחת תנאים שבהם הסיגמה הוא ידוע. לא, רגע, בסדר. היה פה שני דברים, אני קודם עונה על השני שהוא יותר קל. אמרתי שהסיגמה משתנה. אמרתי שסיגמה משתנה, אמרתי, בוא נגיד שעכשיו את מה שמופיע פה בחוקי המשחק, אני הולך ומקטין. זאת אומרת, נגיד שהייתי שם פה איזה פרמטר לפני זה, הייתי כותב אלפא סיגמה 0 של y, ומסתכל על נוירונים כאלה, שפועלים בתנאים שהכמות הרעש יותר ויותר קטנה. אז עכשיו אני כן משנה את זה. אמרתי שכשאני משנה את זה, אז הדבר הזה הוא לא פשוט נעלם, הוא דווקא מתבדר. זה משהו אחר, אבל בואו נעזוב את זה בצד עכשיו. סיגמה הוא נתון.
אבל הוא בכל זאת לא נתון, אם אתה משנה את x.
לא, אוקיי, אז עכשיו השאלה היא, אז כאן צריך להבין למה אנחנו עושים אופטימיזציה. יש ביטוי, כתבתי אותו, שמחקתי אותו עכשיו, אבל מה היה הביטוי? היה בו את ה-L הזה, שזה המינוס אינטגרל P של y, לן P של y, y, מינוס, מה היה שם? חצי אינטגרל של שני של P של y, לוג של שני פאי E, סיגמה בריבוע של y, נכון? עכשיו, בעצם בכלל כשאנחנו כותבים אינטגרלים כאלה, צריך לזכור, ה-y הזה שמופיע פה זה לא כבר זה איזשהו משתנה אינטגרציה, הייתי יכול לקרוא לו גם בשם אחר, אני יכול y קטן. אנחנו עושים אינטגרלים לכל הערכים של y. עכשיו מתמטית, יש פה איזשהו ביטוי מתמטי. ומה שאני שואל זה איך הביטוי הזה תלוי כפי של y. עושים כפי של y. למה בכלל אני חושב שמותר לי לשנות את הפונקציה הזאת? כי אני יודע שכשאני משנה את הפונקציה f, אני משנה גם את פי של y. כי יש איזושהי התפלגות של x, יש איזושהי התפלגות פי של x. פי של x אני מתרגם אותו ל-y דרך איזושהי פונקציה לא ליניארית. וזה בעצם מה שיקבע את פי של y.
כן, שינוי של פי של y משנה את הערכים ש-y יכול לקבל.
נכון, אבל צריך לחשוב על זה מתמטית. מה שמופיע כאן, שוב, זה אינטגרל על כל הערכים האפשריים של y פריים, על כל הערכים האפשריים של y פריים, של איזשהו ביטוי שכולל בתוכו את פי של y, הוא כולל את הפונקציה הזאת סיגמה בריבוע של y. המבנה של, זה נכון ש-y, ההתפלגות של y משתנה, אבל הפונקציה הזאת של y נשארת קבועה.
ביחס למה?
ביחס במצב שבו אני משנה את פי של y. זאת אומרת, תחשבי על זה שנגיד ש-y היה
אם אתה משנה את פי של y, אז גם הסיגמה משתנה, כי הערכים ש-y יכול לקבל הם שונים.
אבל פה יש פשוט איזשהו אינטגרל. מה כתוב פה? פה יש פה סכום על כל הערכים האפשריים של y.
נגיד במצב קיצוני שאתה משנה את פי של y להיות פונקציה דלתא.
אני
חושב שהסיגמה ישתנה, הוא לא יהיה.
לא, אז אני חושב תראי, אני טוען שהפונקציה סיגמה לא משתנה. האינטגרל הזה משתנה. האינטגרל הזה משתנה כי את בעצם, אם נכון, אז נתת דוגמה טובה, אם פי של y הוא רק, יש לו ערך אחד, אז בעצם מה נקבל באינטגרל הזה? נקבל את לן שני פאי e סיגמה סקוור של אותו y. שנייה, אז למה זה השתנה? זה השתנה כי פי של y השתנה. נכון? אבל פה, אבל כשאני גוזר, אז
אתה בודק איך סיגמה y משתנה על ידי שינוי קטן בפי של y.
זה בעצם, אני שואל איך הממוצע של, בעצם מה כתוב כאן? כאן כתוב הממוצע של לן שני פאי e סיגמה בריבוע של y, נכון? ממוצע לפי פי של y.
אבל כשאתה גוזר, יש את החוק הזה עם ועוד, אז אתה צריך לגזור את זה ולכפול בזה.
לא, כי התלות היחידה בפי של y וההסתברות של y מופיעה כאן, היא לא מופיעה כאן.
אבל כן נכתוב בפי של y.
לא, תראי, איפה מתמטית, איפה יש פה תלות בפי של y? לא, y זה פשוט משתנה. יש פה איזה משתנה אינטגרציה. יש פה פשוט אינטגרל. מה כתוב פה?
אבל y הוא משתנה.
כן, y הוא כתוב פה סכום, אם נתרגם את האינטגרל לסכום, נכון? נגיד שזה לא היה, זה דיסקרטיזציה של האינטגרל. אז יש סכום על כל הערכים האפשריים של y, נגיד שהיה לנו את דלטה y, כל הערכים האפשריים של y, פי של y, לוג שני פאי e, סיגמה בריבוע של y פעם. בסדר? עכשיו, זה נכון שכשאני משנה את פי של y, יש ערכים של y שיהיו יותר מסתברים, וזה ישנה את הסכום הזה, זה ישנה בגלל שיהיה להם יותר משקל פה.
זה ישנה את סיגמה.
לא. סיגמה זה איזשהו קשר...
אם הערכים ש-y יכול לקבל את שונים, אז סיגמה משתנה.
הממוצע של סיגמה משתנה. סיגמה עצמו לא משתנה. לא, תראי. לא, תראי. נגיד y, נגיד שהסיגמה של y שווה ל-y בריבוע. בסדר? אז מה כתוב פה? כתוב פה מינוס אינטגרל, מינוס חצי אינטגרל, פי של y, לן 2 פאי היא y בריבוע. dy. y זה משתנה אינטגרציה, מה זה y משתנה? y זה משתנה אינטגרציה, יש לי פה אינטגרל מינוס לא נכון, לא, זה משתנה אינטגרציה, יש פה סכום על כל הערכים.
אם אתה משנה את פי של y,
לא, הוא
הופך מ-0
לא, את מבלבלת בין הערך של y כמשתנה אקראי לבין ממוצע, לבין אינטגרל על כל הערכים. מה שמשתנה, מה שמשתנה זה כל האינטגרל הזה, והוא משתנה לא בגלל של y, הוא משתנה בגלל שההתפלגות של y משתנה. זה נכון שאם y
זה לא ממוצע, זה לא בגלל ממוצע.
זה בדיוק הממוצע.
נעשה את הנגזרת לתוך האינטגרל. לא גזרת את האינטגרל.
לא גזרתי, אני כן גוזר, אני גוזר את כל הביטוי הזה לפי פי של y. אני שואל איך כל הביטוי הזה תלוי בפונקציה הזאת, פי של y.
אבל לא גזרת את זה. לפי מה שיצא לך לא גזרת את האינטגרל.
כן גזרתי את האינטגרל, זה הנגזרת הפונקציונלית. בעצם, כשאני גוזר לפי פי של y ספציפי, אז אני עכשיו גוזר לפי דלטה פי של y, אז באינטגרל הזה מופיעים כל y, ורק כש-y שווה ל-y, רק כש-y פעם שווה ל-y, האינטגרל הזה מושפע מהפי של y הזה, ואז האינטגרל הזה נותן פשוט את המינוס חצי לן 2 פאי אי סיגמה.
אז באמת אינטגרל,
לא, לא. אוקיי, אז אני חושב, מה שבעצם חסר לך זה ההבנה יותר של הנגזרת של מה שנקרא נגזרת פונקציונלית של אינטגרלים.
כן, למדנו את זה
אני יודע, בדיוק, זה קצת קצר מדי. ואני חושב שזה המקור לבלבול, זה באמת דבר מבלבל. בפיזיקה עושים את זה הרבה בשנה השנייה של הלימודים, עושים את זה בהרבה הקשרים ובסוף מבינים את זה. אני חושב כאן נעוצה הבלבול, שתבין אותו. אני פשוט עכשיו יש לי בשיחת סקייפ, אז אני לא יכול להמשיך להסביר לך, אבל זה חשוב ש... מה שצריך לעשות קודם זה לעבור לדוגמאות יותר פשוטות של נגזרת פונקציונלית. אולי הדברים שעשיתם בתרגול, ואני בשמחה אעבור איתך על זה ביחד. ואני חושב שאחרי שתביני אותם יותר טוב, הקושי לפי דעתי, הוא בהבנה מה בעצם אנחנו עושים כאן כשאנחנו עושים מה הכוונה שאני חושב את הדבר הזה. זה באמת לא דבר...
אם זה משהו מאוד ספציפי, אז לא דבר.
אבל אני חושב שכאילו, העובדה שאת לא מבינה זה דווקא בגלל שאת מנסה להבין, אוקיי? כי לא יודע, זה בסדר.
אז כאילו יש לך פה רק S1 כאילו מתוך בעצם כל האינטגרל הזה, נכון? כל היתר כאילו אתה מסתכל בעצם רק על S1, זה כמו שיהיה לך בעצם מהאקסוס של דלטה.
זה ממש נגזרת על אינטגרל של סוגי שמותת אינטגרל.
זה כאילו, האינטגרל הוא על כל ה-y, ואתה גוזר לפי פי y, שפי y הוא נגיד של פי y זה כאילו, גוזר על y ספציפי.
זה בעצם כמו שהיינו גוזרים לפי y ולא לפי פי של y. זה לא אותו דבר, אבל...
לא, הפונקציה שלך, זה שאני הבנתי.